Okay, sir, understood.
Okay, so let's move on. The next example is the dihedral group. And the geometric or the physicist notation of that is Dn. The abstract algebra notation or the mathematics notation of that is D2n. So there's a, oops, sorry. Okay, so the dihedral group say D of n is the symmetry group. So I'm cheating and defining it as a symmetry group of something. The symmetry group of an n-sided regular, say, polygon, without directed sides. Okay, so what do I mean? So if I go back to my pentagon, if, for example, I didn't have these arrows, if I didn't have these arrows, then the symmetry of this object would be greater, right? Do you agree? If there were no arrows here?
Yes, sir.
Because then we discrete reflections. The arrows stop us from doing reflection. So if I have arrows and if I do a reflection, say around this axis, say, let me say around this axis in the middle, around the y-axis, imaginary axis, then these arrows don't go to each other. The arrows flip their orientation, right? Whereas this arrow gets very confused. It doesn't know what to do, right? So if I put the arrows, the symmetry of this object is reduced. So if there are no arrows, then the symmetry is increased. And so it should be kind of obvious that Cn is a subgroup of Dn. Okay? Because we still have those rotations. Now, to understand the structure of this group a little bit better, I'm going to appeal to geometry, and I'm going to introduce the notion of a median. So what is a median? If n is even for a polygon, a regular polygon, medians are lines that go through opposite vertices, say opposite vertices, and bisect. There should be probably an Oxford comma here, and bisect opposite sides, or bisect opposite sides. So if I draw, let me just do the easy drawing. Let's take a square. Sorry, it's not a very good square. So the medians are, this is a median. This is a median. Oops, sorry. This is a median. Sorry, this is not a very good median. Let me just, yeah.
So there will be 8 medians.
No, there are 4 medians.
Oh, okay, I
1,
double counted.
2, 3, 4. Yes, it's very common to do that. So don't feel bad. So the number of median is equal to the n. Okay. Now, if n is odd, then we have only one type of median. Okay, so if n is odd, then the median is a line that medians are lines that bisect a side and go through the opposite vertex. Okay, so if I have, say, a triangle, a equilateral triangle, then you know, the medians would be just these. Again, I'm not able to draw for some reason. And now the moment of truth. Yeah, that didn't work. Okay, so there are 3 medians, right? So the idea is that if you're dealing with, say, Dn, so that we have an n-sided, you know, regular polygon, then it has n medians. So what do medians do? See that reflection around any of the median is a symmetry. Okay, this is something we didn't have for the directed sides because reflection screwed up the symmetry, right? So reflections, you know, around medians give us new symmetry operations. New in addition to the ones in CN, right? Okay.
Would you please explain what you meant by direct sum symmetry broken? Direct multiplication symmetry?
Not direct multiplication, the directed sides. Similar, if I have directed sides.
Oh, the arrows. Okay, got it.
Yeah. No.
Sir, you wrote that the n side of regular polygon has n medians, but won't that depend on n being even or odd? Like it's just a line again.
No. Yeah, because if it's odd, I mean, look at the triangle, how many medians does it have? The way we have defined it, it has exactly 3 medians.
Oh yeah. Oh, sorry.
Okay. Yeah. So medians are essentially axes of symmetry of reflection. Okay. Now, it's not obvious, but the way to, you know, we can define Dn in the following way. So Dn consists of all the Cn's. Here I'm going to borrow very heavily from, say, Hugh Osborne. So it consists of all the elements of Cn. So where R, you know, goes from 1, you know, R goes from 0, 1, n minus 1 with, you know, a to the power n is e. So this is what I mean. You know, But it also consists of, all the B's, one B, one of the reflection around the median. It doesn't matter which one. You can pick, but you just pick one. One of the B's, and of course, reflection, around the B twice is going to give you E, right? Because if you reflect twice, you get the same thing. And it is not difficult to show that alpha times beta or B is, if you first reflect and then rotate, is the same thing as rotating n-1 times and then reflecting. Okay, and then all the B's with all the ARs. Okay, so R goes from 0, 1, ... n-1. So, sorry, this is not a very neat, like looking definition, but let me just break it up. So we have Cn as a subgroup of Dn, right? So Dn has in it C of n. But it also has one of the reflections B, as well as, all the B's and all the alphas times alphas. So one of the B's and times alphas, where, R goes from 0, not 0, R goes from 1, ... n-1. Okay. So this has order n, and then this adds n more elements, so that the order of D of n is 2n. So there are 2n elements. And remember, the order of Cn was n. And the comment I wanted to make before take question is that, mathematicians or abstract algebra people, call Dn D2n. Okay, so there's a change. What we're calling Dn, they call D2n. They're actually honest about the order of the group. Here, we are talking about because we are physicists, we are relying on the number of sides the polygon has, because we always need the crutch of having something very definite. Okay, so let's take some comments, because I'm sure everybody's confused.
Sorry, about the rotational axis of a square. Did we consider only the same plane rotation? Because if the square is
Yes.
on a 2D plane, the third z-axis would also make a rotation.
Yeah, but that, then you can add as many dimension as you want, right? So why just stop at 3? But no, the definition just says that you're restricted to 2-dimensional plane.
Okay, got it.
Yeah.
Sir, so the rotations in Cn, like they're they're 2-dimensional rotations, but the
Yes.
rotations in Dn that are that we have added later on, they basically require an extra dimension, right?
But they're reflective, they're not rotation. You can think of it as a rotation.
Okay.
As
okay. So we're saying reflection is a different operation.
Yeah, it's a discrete operation.
And then if we just added B, then we could have created the reflections along other medians by composing that reflections.
Exactly. Yeah, and that's basically, I'm going to do that very explicitly now with an example. Okay.
Okay.
So any other questions? Because I want to explain how just one median can do the job with, and illustrate that with an example. You can also prove this, it's not very difficult, but I have not prepared a proof. So let's, and that's kind of the spirit of this class. I'm not going to be bothered very much about proofs. You know, it'll be, but you know, we will prove some theorems, such as isomorphism theorems. So let's take D4. Okay, so D4 is going to be the dihedral group, which is the symmetry group of the square. And let me draw the medians with blue. So we have a median here, median here. All right, it's good enough. Yeah. All right. So let me label the vertices. So this is vertex number 1, 2, 3, 4. So there is some sort of, you know, the idea is that each vertex, these vertices can exchange places. And if they do, if there's an operation under which these vertices exchange places, then that's a symmetry operation. And let's call this median B and this one say B prime. Okay, so C4, which is a subgroup of D4, consists of, say, rotations, which are 2 pi I n over 4, where n is, say, 0, 1, 2, 3. Well, it can be anything. But these are the 4 unique elements. So under rotation, you know, so this is, okay. And so if alpha is 2 pi I over 4, so under alpha, you know, vertex 1 goes to 2, sorry, you know, 1 goes to 4, right? Yeah. So 1 goes to 4, 4 goes to 3, 3 goes to 2, 2 goes to 1. Okay? Now, let's look at B. What does B do? So if I apply B, then, so basically reflection around the B axis, then 2 goes to 2. 2 doesn't change. And 4 goes to 4. But 1 goes to 3, and 3 goes to 1. Okay, so let me copy this picture and paste it over here. So the resulting, what happens is that, you know, the vertex number 1 comes here and 3 goes here. Okay? Right. So now if I look at it, see the ordering here was, you know, if I went, say, clockwise 1, 2, 3, 4. But now that we have made a reflection, the order is 1, 4, 3, 2. Okay? So the ordering has changed. So there's no way that, you know, so essentially, you know, that's what happens when you reflect in a mirror, right? You cannot get from this picture to this picture by any rotation. Alpha is not going to take you, however many times you apply it, it's not going to take you from here to here. Is that clear?
Yes, sir.
Yes, sir.
I had a question. Like B prime should be like the vertical axis now, right? In the second figure.
No, I mean, I'm not changing the, those are not part of the diagram. Those are not part of the shape.
Okay.
Okay. So now if I say make a, if I make a rotation around, if I reflect around B prime, I just wanted to show that, reflect why one axis is good enough. Because you might say, okay, if I want to get back to the same ordering as before, I would have to necessarily do a reflection around B. I'm going to say no. Just like, what if I now do a reflection around B prime, then what will happen is that 1 will go to 2, and 2 will go to 1, and 3 will go to 4, and 4 will go to 1. And now if I draw this, so this was 1, 2, 3, sorry, let me just draw the picture before. So this was 1 went to 2. So 1 is now here. And 2 went to 1. So this is here. This is 4. And this is 3. Right? So we see that we are back to the same ordering as before, right? So this is basically my way of telling you that, you just have to pick one of the vertices to reflect around, and you are going to get all the, and then if you apply alpha, so if you multiply by B and then apply some alpha to the power R, you're going to get all the other elements. So you're not going to get new elements by, say, applying B prime and alpha to the power, say, R prime. Okay, so the one median is enough. That's all I wanted to say. I'm not sure if this is clear from the way I've presented it. Another way of doing it would be if I started from the original picture and did the reflection around B prime, the ordering, the relative ordering of the points would be the same as the relative ordering we got from reflecting around B. And you can verify that. Okay?
I'm actually a little confused. Which two actions did we compose?
Reflection and rotation.
I see.
So yeah, let me just like make a statement, like Dn consists of all rotations, generated by alpha, that is, any power of alpha, and a reflection about one of the medians, say B, followed by rotations. Okay?